The year is 1916, and the trenches of the Western Front have become laboratories of desperate innovation. The German Empire, locked in brutal stalemate against Allied forces, is discovering that the weapons carried into this war, rifles designed for 19th century tactics, machine guns too heavy for mobile warfare, pistols inadequate for close-quarters trench fighting, are ill-suited to the reality of industrial warfare fought in muddy ditches across a devastated landscape. Every combatant nation is frantically improvising, modifying, and experimenting with weapons that might provide some tactical advantage, some edge that could break the deadlock. Among the German experiments during this period is one of the most unusual and least known weapons modifications of the entire war, the attempt to transform the Bolt-Action Dreyse Rifle into a weapon approaching light machine gun capability by fitting it with the 25-round box magazine from the MG13 light machine gun. The Dreyse rifle itself carries a distinguished lineage in German military history. The Dreyse name is most famous for the Dreyse needle gun, the Zündnadelgewehr, which was the first bolt-action military rifle adopted by any major military power, entering Prussian service in 1841. The needle gun gave Prussian infantry a decisive advantage in the wars of German unification during the 1860s and early 1870s, allowing them to fire from prone positions and reload far faster than enemies using muzzle-loading rifles. By the time of World War I, however, the Dreyse rifles in service are later designs from the Rheinische Metallwaren- und Maschinenfabrik, commonly abbreviated as Rheinmetall. These rifles, sometimes designated as the Dreyse Model 1907 or variations thereof, are bolt-action repeating rifles firing smokeless powder cartridges from internal magazines holding 5 to 10 rounds depending on the specific variant. The Dreyse rifles of World War I are secondary weapons in the German arsenal, supplementing the primary service rifle, the Gewehr 98, designed by Paul Mauser and adopted in 1898. The Gewehr 98 is the standard German infantry rifle, produced in the millions, but wartime demand for rifles exceeds production capacity. Germany turns to secondary suppliers and alternative designs to arm its rapidly expanding military. Dreyse rifles are issued to reserve units, fortress troops, and second-line formations. They are functional, reliable weapons, but they lack the prestige and the production priority of the Mauser rifles. This secondary status makes them candidates for experimental modifications that might not be attempted with frontline Gewehr 98s. If the modification fails or produces an impractical weapon, the loss is less significant. The MG13 light machine gun that provides the 25-round magazine does not yet exist in 1916. It will not be developed until the 1930s as part of German rearmament under the Nazi regime. This presents an immediate chronological problem with the scenario as stated. The weapon being described is likely a confusion or conflation of several different German weapons development programs from different periods. However, to explore the concept of fitting a 25-round detachable box magazine to a World War I-era bolt-action rifle, we must look at the actual historical experiments that did occur, which involved various attempts to increase ammunition capacity in bolt-action rifles using detachable magazines from light machine guns and automatic rifles of the period. During World War I, the German military does experiment with extended capacity magazines for bolt-action rifles. The trench magazine for the Gewehr 98, discussed in a previous examination, is one such experiment. Other efforts involve adapting magazines from the Madsen light machine gun, experimenting with extended magazines for the Bergmann MP18 submachine gun, and exploring various high-capacity feeding systems for rifles. The fundamental challenge is that bolt-action rifles are designed with internal magazines holding 5 to 10 rounds, loaded via stripper clips. Adapting these rifles to accept large-capacity detachable magazines requires substantial modifications to the rifle's stock and receiver, and the resulting weapons often prove awkward and impractical. Let us construct a historically plausible scenario. German weapons designers in 1916 or 1917 attempting to create an improved rifle for trench warfare by fitting a Dreyse rifle with a 25-round detachable box magazine similar in design to those used on contemporary light machine guns. This magazine might be adapted from the Madsen, or it might be a purpose-designed magazine created specifically for this experimental rifle program. The goal would be to provide riflemen with substantially increased ammunition capacity without the weight and complexity of belt-fed machine guns, creating a weapon that bridges the gap between standard rifles and automatic weapons. The Dreyse rifle's bolt action is similar in principle to the Mauser design, a manually operated rotating bolt that locks into the receiver via lugs. The shooter lifts the bolt handle to unlock, pulls rearward to extract and eject the spent casing, pushes forward to chamber a fresh round, and rotates down to lock. This action is reliable and proven, but it is fundamentally slower than semi-automatic or automatic fire. The rate of fire for a bolt-action rifle operated by a trained soldier is perhaps 15 to 20 rounds per minute under ideal conditions, though sustained fire at this rate is exhausting and accuracy degrades rapidly. Compare this to a light machine gun firing at 400 to 600 rounds per minute, and the fundamental limitation of bolt-action rifles in sustained fire rolls becomes apparent. Creating a 25-round magazine for the Dreyse rifle requires addressing several engineering challenges. The standard Dreyse rifle has an internal magazine that is part of the stock and receiver assembly. Converting to detachable magazine requires machining or modifying the stock to accommodate a magazine well and designing a magazine catch mechanism. The magazine itself must be designed for the specific cartridge the Dreyse fires, likely the 7.92 by 57 mm Mauser round that was standard for German military rifles, and most present cartridges at the correct angle and height for the Dreyse's bolt to strip them reliably. A 25-round box magazine for 7.92 by 57 mm ammunition is substantial in size and weight. Each cartridge weighs approximately 25 grams, meaning 25 rounds represent roughly 625 grams, about 1.4 pounds of ammunition alone. Add the weight of the steel magazine body, spring, and follower, and a loaded 25-round magazine weighs approximately 2 pounds. The Dreyse rifle itself weighs approximately 9 pounds empty. Adding a 2-pound magazine brings the total to 11 pounds, a noticeable increase that affects how the rifle handles and how tiring it becomes to carry during long operations. The physical dimensions of a 25-round magazine create handling issues. To hold 25 rounds of full-power rifle ammunition, the magazine must be either very long in a single-stack configuration or somewhat shorter but wider in a double-stack configuration. A single-stack 25-round magazine for 7.92 by 57 mm might extend 8 to 10 inches below the rifle's stock, creating the same prone position interference problems discussed with other extended magazines. A double-stack magazine would be shorter but wider, creating bulk that interferes with carrying and handling in different ways. Either configuration represents a compromise between capacity and practicality. Loading a 25-round rifle magazine is significantly time-consuming than loading the standard 5-round internal magazine via stripper clip. With stripper clips, a soldier can load 5 rounds in a few seconds, insert the clip into the guide, press the cartridges down into the magazine, remove the clip, repeat if additional rounds are needed. Loading 25 rounds into a detachable magazine requires inserting each cartridge individually against spring tension, a process taking 2 to 3 minutes for the full magazine. This means that while the magazine provides more rounds before the first reload, that first reload takes far longer when it comes. The tactical employment must account for this. Magazines must be loaded in advance, and running out of ammunition during an engagement means either having preloaded spare magazines immediately available or accepting a lengthy vulnerable period while reloading. The feeding reliability of a 25-round magazine in a rifle designed for 5-round internal magazine feeding is questionable. The Bolt's feeding geometry is optimized for cartridges presented from a short stack at a specific angle. A tall stack of 25 cartridges in a magazine introduces variables. The feeding angle may change as the magazine empties. Spring tension may vary. The follower may bind in the magazine body. Each of these potential issues can cause feeding failures. The longer the magazine, the more opportunities for problems. Light machine guns designed from the start to use such magazines have actions engineered to accommodate the feeding geometry and potential variations. A bolt-action rifle retrofitted with a high-capacity magazine may experience frequent malfunctions. Environmental conditions in trench warfare are spectacularly hostile to mechanical reliability. Mud penetrates every opening, coating internal mechanisms and working its way into magazines. The 25-round magazine, with openings at top and bottom and internal spring mechanism, is vulnerable to contamination. A magazine filled with mud ceases to function, and cleaning it thoroughly enough to restore reliability requires disassembly and careful cleaning of all internal surfaces, difficult in rear areas, impossible in front-line trenches under fire. Soldiers would need to protect magazines from contamination, carrying them in waterproof pouches or covers, adding bulk and complexity to their equipment load. Assuming German engineers overcome these challenges and create a functional Dreyse rifle fitted with a 25-round magazine, the question becomes, what tactical purpose does this weapon serve? It provides 25 rounds before reloading, compared to 5 or 10 in standard rifles, a substantial capacity increase. But it is still a bolt-action rifle requiring manual cycling between shots. The rate of fire remains limited to what a trained soldier can achieve working the bolt, perhaps 20 rounds per minute sustained, with accuracy degrading as the soldier fatigues. Compare this to the MP-18 submachine gun, entering service in 1918, which fires automatically at 400 rounds per minute from a 32-round magazine. Or the MG13 light machine gun, which fires at 500 rounds per minute from belts. The tactical niche for a bolt-action rifle with extended magazine is narrow. One potential application is providing increased firepower to soldiers in defensive positions where the weight and bulk of the magazine are less problematic. A soldier defending a trench segment or bunker entrance could use the 25-round magazine to maintain fire against attacking enemies without frequent reloading. The bolt-action fire rate, while slower than automatic weapons, still allows engaging multiple targets if the soldier works the bolt smoothly. The extended magazine means fewer vulnerable moments while reloading, potentially allowing a single defender to hold a position that might otherwise require 2 or 3 soldiers with standard rifles. Another potential application is for marksmen or snipers who need to engage targets at ranges where the rifle's accuracy remains effective but want more rounds available before needing to displace to avoid counterfire. A sniper with a 25-round magazine can engage multiple targets in succession before needing to displace to avoid counterfire. This assumes that working the bolt between shots does not disrupt aim significantly. A trained marksman can work the bolt smoothly while maintaining sight picture, allowing rapid follow-up shots on different targets. However, both of these applications are better served by purpose-designed weapons. Defensive positions benefit more from actual machine guns that provide sustained automatic fire. Marksmen and snipers typically prioritize concealment and single precise shots over volume of fire, making standard rifles with small magazines more appropriate than bulky extended magazine configurations. The experimental magazine-fed Dreyse rifle occupies an uncomfortable middle ground, more capable than a standard rifle but more awkward, less capable than automatic weapons but available in greater numbers. Whether this middle ground represents useful capability or merely expensive compromise depends on specific tactical circumstances. German soldiers testing experimental magazine-fed rifles report mixed reactions. The increased capacity is appreciated, particularly by soldiers who have experienced the desperate moments in combat when ammunition runs out and enemies are still advancing. The ability to fire 25 times before reloading provides psychological reassurance as much as tactical capability. Knowing that the weapon holds sufficient ammunition to deal with threats reduces stress and allows more aggressive tactical decision-making. But the weight, bulk, and handling awkwardness generate complaints. The magazine interferes with movement through trenches, catches on obstacles, digs into the ground when firing from prone position. The rifle feels unbalanced with the heavy magazine extending below the stock. Reloading the magazine is tedious and time-consuming. The reliability issues prove particularly frustrating. In testing range conditions with clean weapons and fresh ammunition, feeding malfunctions are tolerable, perhaps 1 or 2 failures per magazine. Under field conditions with weapons exposed to mud and soldiers operating under stress, malfunction rates increase to unacceptable levels. A rifle that jams every 5 or 6 rounds is worse than useless. It is actively dangerous, leaving soldiers unable to return fire at critical moments. Clearing jams in bolt-action rifles requires cycling the bolt to extract the jammed round, which may itself be difficult if the round is wedged in the chamber or if the bolt is fouled with mud. These reliability problems plague extended magazine rifle experiments across all combatant nations during World War I and contribute to abandonment of most such programs. The manufacturing resources required to produce 25-round magazines are substantial. Each magazine requires precision stamping of the magazine body, forming, welding, spring manufacture, and follower fabrication. Quality control is critical. Magazines with out-of-tolerance dimensions cause feeding failures. German industry in 1916 to 1918 is stretched to maximum capacity producing rifles, machine guns, artillery, ammunition, and countless other war materials. Adding production of complex detachable magazines for experimental rifle variants competes for resources with higher priority needs. Unless the experimental rifles prove decisively superior to existing weapons, allocating scarce manufacturing capacity to magazine production is difficult to justify. The logistics of supplying and maintaining detachable magazines present challenges that stripper clip-fed rifles avoid. Stripper clips are inexpensive stamped metal items that can be discarded after use without significant loss. Detachable magazines are expensive precision items that must be recovered, cleaned, inspected for damage, and redistributed. Military logistics systems must track magazine inventories, ensure units receive adequate supplies, and establish procedures for magazine recovery from casualties and battlefield losses. This logistics infrastructure does not exist for rifle magazines in 1916. It must be created from scratch, adding complexity to an already strained supply system. As the war progresses and weapons technology evolves, the tactical niche for high-capacity bolt-action rifles continues to narrow. The MG13 submachine gun proves that automatic fire in a man-portable package is achievable and effective for trench combat. Light machine guns, like the MG08-15, prove that squad-level automatic weapons support is practical. These purpose-designed automatic weapons perform their roles better than modified bolt-action rifles can, and military procurement naturally prioritizes them. Experimental programs involving extended magazine bolt-action rifles are gradually deprioritized, with resources redirected toward automatic weapons production. By the time of the armistice in November 1918, most experimental magazine-fed bolt-action rifle programs have been discontinued or reduced to minimal effort. The few surviving examples of experimental magazine-fed bolt-action rifles from the World War I era exist primarily in museum collections specializing in German military history or in the hands of serious collectors who understand their historical significance. The interwar period sees continued experimentation with high-capacity magazines for rifles. But the focus shifts towards semi-automatic and automatic rifles designed from the start to use detachable magazines rather than bolt-action rifles retrofitted with them. The German military explores designs that will eventually lead to weapons like the Gewehr 41 and Gewehr 43 semi-automatic rifles, both of which use detachable box magazines. These weapons demonstrate that the concept of rifle-caliber weapons with detachable magazines feeding powerful cartridges is sound, but the implementation must be integrated into the weapon's design from the beginning rather than grafted on to existing bolt-action designs. The MG13 light machine gun, referenced in the scenario, is developed in the early 1930s as part of clandestine German rearmament in violation of Versailles Treaty restrictions. The weapon uses a 25-round box magazine feeding 7.92 by 57 mm ammunition, and it represents an evolutionary step in German light machine gun development between World War I-era weapons and the revolutionary MG34 and MG42 designs of World War II. If weapons designers in the 1930s had attempted to fit an MG13 magazine to a bolt-action rifle, whether a Dreyse or a Gewehr 98, they would face all the same challenges encountered during World War I experiments, with the additional knowledge that semi-automatic rifles like the developing Gewehr 41 offered superior solutions to the same tactical requirements. Modern firearms collectors and military historians who study obscure experimental weapons occasionally encounter references to magazine-fed bolt-action rifles from the World War I period. These references are often fragmentary, a mention in an ordnance report, a photograph of an unusual-looking rifle, an oral history from a veteran who recalls seeing such weapons during training. Reconstructing the complete history of these experimental programs is difficult because many records were lost during the chaotic end of the war, deliberate destruction of documents under Versailles Treaty terms, and subsequent destruction during World War II. The weapons themselves, produced in small numbers for testing, have mostly disappeared, destroyed, converted back to standard configuration, or lost to time. The few surviving examples of experimental magazine-fed bolt-action rifles from the World War I era exist primarily in museum collections specializing in German military history or in the hands of serious collectors who understand their historical significance. These weapons are valued not because they represent successful designs that saw widespread service, but because they illustrate the experimental process, the challenges of weapons development under wartime pressure, and the evolutionary dead ends that inform understanding of how successful weapons emerged. The story of attempting to fit a 25-round magazine from a light machine gun into a bolt-action rifle illustrates several enduring principles of weapons development. First, it demonstrates the challenge of adapting existing weapons to roles they were not designed to fill. Bolt-action rifles were optimized for deliberate, aimed fire at individual targets, with ammunition capacity sufficient for that purpose. Attempting to transform them into sustained fire weapons by simply adding larger magazines ignores the fundamental limitations of the bolt-action system, the requirement for manual operation between shots, the feeding geometry optimized for short magazine stacks, the structural design that assumes certain weight and balance characteristics. Second, the story reveals the importance of considering the complete weapon system rather than individual components in isolation. A 25-round magazine might function adequately when tested separately, but when integrated with a rifle designed for different magazines, the system-level problems emerge. Weight distribution changes, balance shifts, handling characteristics alter, feeding reliability decreases. The magazine that works well in a light machine gun designed to use it may work poorly in a rifle retrofitted to accept it. Successful weapons design requires holistic consideration of how all components interact. Third, the experimental magazine-fed bolt-action rifles demonstrate that interim solutions can serve important developmental purposes even when they never reach production. The knowledge gained from testing these weapons, understanding what does not work and why, informs subsequent development programs. Engineers learn about magazine design, feeding geometry, and the practical limitations of various configurations. This knowledge prevents future wasted effort on similar, unpromising approaches and guides development toward solutions that actually address tactical requirements effectively. The contrast between experimental magazine-fed bolt-action rifles and the weapons that ultimately succeeded in their intended roles is instructive. The MG13 submachine gun succeeded because it was designed specifically for automatic fire in close-quarters combat, with every aspect of the weapon optimized for that purpose. The MG34 and MG42 light machine guns succeeded because they were designed from the start for sustained automatic fire using appropriate feeding systems and mechanical actions. These successful weapons did not attempt to transform existing designs into something they were never meant to be. They started with clear tactical requirements and engineered solutions specifically to meet those requirements. When German weapons designers attempted to put a 25-round magazine from a light machine gun into a bolt-action rifle, whether a Dreyse or any other bolt-action design, they were attempting to solve a real tactical problem with the tools and knowledge available to them. The increased ammunition capacity was genuinely desirable. The concept of giving riflemen more rounds before reloading addressed actual combat needs. But the implementation approach proved impractical. The resulting weapons were heavier, more awkward, less reliable, and still fundamentally limited by the bolt-action operating system's inherent rate-of-fire constraints. The experimental magazine-fed bolt-action rifles represent a developmental dead end, an approach that was tried, tested, and ultimately abandoned in favor of better solutions. They serve as historical examples of how weapons development proceeds through experimentation, how not every promising idea proves practical when tested, and how the process of elimination is as important to successful development as the process of innovation. The rifles themselves may have disappeared into history's dustbin, but the lessons they taught about magazine design, feeding reliability, the limitations of adaptation, and the importance of integrated systems design contributed to the development of successful weapons that did serve effectively. The story reminds us that military innovation during wartime is often characterized by desperate experimentation, by trying anything that might provide an advantage, even when practical considerations suggest an approach is unlikely to succeed. The pressure to find solutions is intense, the tolerance for failure is low, but the need to explore options is paramount. Some experiments succeed and transform warfare. Others fail and are forgotten. The magazine-fed bolt-action rifle experiments fall into the latter category. Interesting historical footnotes that illustrate the development process without themselves contributing to operational capability. And that, too, is valuable knowledge. Understanding what was tried and why it failed helps prevent future repetition of the same mistakes and guides development toward approaches with better prospects for success.